So today we're going to learn how to integrate by substitution. And integration by substitution, it's basically the first integration technique you learn, and it's very, very useful. And it's kind of related to the chain rule for derivatives. It doesn't work exactly the same way, but you should remember the chain rule to make this easier. So first off, let's start off with let's say we're trying to find the integral of for example 2x e to the x squared dx. Now if you look at this, well, we don't have a rule for when we have a product. We're integrating a product, and so we think about this, and well, if we just kind of remember what this is asking us to find, it's asking us to find the antiderivative of this function right here, 2x e to the x squared. So that basically means that we're looking for a function that when I get the derivative of it, it equals this. So we think, and well, why don't we try to guess? Okay, so let's try to just kind of guess, and well, I'm gonna help you out with this first one. My guess is gonna be that the antiderivative of this is e to the x squared. Well, why don't we check it? Well, the derivative of e to the x squared, well, remember that is, let me write this out. So the derivative with respect to x of e to the x squared, well, this is just equal to itself, e to the x squared, times the derivative of the inside, which is x squared, by the chain rule, right? And we notice that this guy is exactly this, and so then we go, ooh, that's right. Wow, I'm so smart. And remember, since we're looking at the indefinite integral, we would add some constant, but when we get the derivative of this constant, this is still equal to this guy. So we're still happy. Happy face? Ooh, blue eyes. Okay, so, oh, and how about a mustache? Wow. Really happy mustache, man. Purple mustache. Okay, anyways, we decided that, okay, we guessed and we got it correct. Well, that's good. But let's take a look at what led us to figure this out. Well, notice that we know how to find the antiderivative of e to the x just by itself. So this guy wouldn't be a problem. The antiderivative is just itself. But here we have e to the x squared. Okay, but notice that the derivative of the inside of the exponential function is actually on the outside of the exponential function as well. So this guy is the derivative of the inside, which is right there. Okay, so this gives us some clues. Well, why don't we try to do one that's similar? So this is problem 1. But slightly different. Let's say we're looking for the integral of just x e to the x squared dx. Okay, so if we try to do the same thing, well, notice that we run into a bit of a problem, because well, it can't possibly be the same one. So let's say we guess, our guess is e to the x squared plus c. And we check and we go, the derivative of e to the x squared plus c, well, I know that's e to the x squared times 2x. So if we compare these, we notice, okay, this is not right. So we go, ooh, sad face. But we're on to something because, well, what we need is, we're just off by a constant. And we're just off by this 2. So what if we change our guess? Instead of being e to the x squared, what if we make it e to the x squared over 2 plus c? Okay, so when we check, we're going to get the derivative of e to the x squared over 2. So the derivative of this guy will, divided by 2, this is just a constant, so I don't have to use the quotient rule. But when I divide by 2, notice that the 2's cancel, and what I end up getting is e to the x squared times x, which is exactly this guy right here, and so that turns my frown upside down. So you'll notice that I've got the sniffles, so I'm a little under the weather, but you guys will forgive me for that, right? Just a couple sniffles. And so this makes me happy. Wow, I even have a bigger happy face than the one before. Okay, so this tells me that, well, constants aren't really a big deal. Now, integration by substitution is basically formalizing this idea. It's kind of like the chain rule for integrals. And the main thing that you notice is that the derivative of the inside is also on the outside. And we learned from this problem down here that we don't worry about constants because we can always add a constant. Okay, so we're going to do problem number 2 again, and we're going to do it by substitution. And so you're going to see that we're going to get exactly the same result. Okay, so now we have the integral of x e to the x squared dx. Okay, so now the first thing you do is you're going to pick your u. And so what you want your u to be is almost always going to be inside, the inside part of your function. So you look at this guy and you go, ooh, I know the antiderivative of e to the x, but not e to the x squared. So we let u be the inside. So we're going to let u be x squared. Okay? So step 1, let u be the inside function. And then the next thing we're going to go do is find the derivative of u with respect to x. In this case, with respect to x, if these were all t's, it would be with respect to t. But it doesn't really matter. So the derivative of u with respect to x is 2x. Okay, now what we're trying to do is we're trying to replace everything that's x here with u's. And so since here I have the differential with respect to x, and I'm going to change everything to u's, what I need to do is also change this into du. So what I'm going to do is I'm going to solve for du here. So du, if I multiply both sides by dx, I'm going to get that du is 2x dx. Okay, so this is going to be step 3, solve for du. Okay, now the next thing is we're going to substitute u and du. And remember, when you're doing this, the whole thing about this is that you're looking for whatever you pick your u to be, you want du to also be in there. And just like in this problem, problem number 2, when we went through this, we don't worry about constants. So here, let's put a big fat star right here. Don't worry about constants. And we're going to see why in a second. Now notice that here we have this guy right here represents u. Okay, so let's start building here. So we're going to have the integral e to the u. Now here I have an x and a dx. What I want is for everything else to be du. So check this out. What I can do, since I want a 2x dx, this is what I want. I want to have a 2x dx inside of here. Notice I have an x dx. So what I can do is multiply by 2, because that's what I need, as long as I balance it with multiplying by 1/2. Now I'm allowed to do this because, well, 1/2 times 2, well, that's just 1, and I can always multiply an expression by 1 if I feel like it, because I'm not changing it. But now, check this out. This 2x dx put together is du. And so then what I have is du, and then I have an extra 1/2 on the outside. And this, I have accomplished my goal. My goal is to change every x into u and make sure I have du in here. And once I do that, then I can find the antiderivative of this guy, which I actually know. This, remember, 1/2 is just a constant, so I don't worry about it. But the antiderivative of e to the u is e to the u plus some constant. And then I can go back to what u equals. Well, u equals, up here I have it, u equals x squared plus c. And notice that this guy is exactly the same guess that I had back here when I did the guess and check method that worked. Now you might be thinking, well, the guess and check is much easier than substitution. Look at all those steps. But the guess and check isn't going to work when it gets harder. So this is a very, very important technique. Now here we went really slow to make sure that we got all the steps down. But later on in a second, we're going to do some that are quite a bit more difficult, and after you get used to it, we'll be able to go a lot faster. But let's write down the other steps that we didn't write down. So here, substitute u and du. Then what we did is we found the antiderivative. And then the last thing is we plug back what u equals with respect to x. And that was it. We're done. Thumbs up. Thumbs up. Thumbs up. Excellent. And then you get a big fat smiley face. Okay. So now we're going to do another one. We're going to step it up a notch. So we're going to do... Oh, can you see that? No, you can't see that. My smiley face went on to the next page. That's how happy it is. It transcends pages. Okay, so this is going to be example number 3. Okay, we're going to find the integral of ln of x over x dx. Okay, so now remember, the reason what tells you to use substitution is that you see that a function in here, if you can find its derivative also inside, and that takes care of all the parts of the integral. If you can find that, then that means that it's probably doable by integration by substitution. And that's what you're going to let u be, whatever it is that you can find the derivative for. So notice that, well, we know, don't we know that the derivative of natural log of x is 1 over x? So that seems like a perfect candidate because, well, also remember, we don't know how to find the integral of natural log of x. We haven't seen it at all. So this seems like a perfect candidate. So if we let u be natural log of x, then du over dx is equal to 1 over x. And if we solve for du, we're going to get 1 over x dx. And so if you take a look, well, okay, then we can go back and substitute. We notice, ooh, this guy is u. And at first, don't get discouraged if you make the wrong choice or if it seems like it takes you nowhere. Integrals are very much a trial and error process in the beginning. So, you're going to try some stuff and maybe you make a mistake, but with practice, you'll learn to recognize a lot faster what it is you need to do. Okay, so we notice that here we have dx over x, which is basically this guy. So this whole thing right here is equal to du. Okay, so now we can go back and change it all into, so the integral of u du. And this we can find the antiderivative of it easily. I mean, the integral of just u, that I can just use the power rule. This would just be u squared over 2 plus c. And then if I go back to what u equals, u is ln of x. So this is just ln of x, the entire thing squared, divided by 2, plus some constant c. And that's it. Okay, now, here's another question. Is that question? How do we deal with limits of integration? So far we've only had indefinite integrals. But we can also have, we can also use this for definite integrals. But if you have a definite integral, those values are with respect to the variables that are inside in the beginning. If you change everything to u's, then those limits of integration no longer are valid. So here you have two options. So let's do an example. Let's say we want to find the integral of x times 5x squared plus 3 to the 10th, and let's say we want to go from 0 to 1. Okay. Now here are your options. Option 1, so here we're going to write down the answer. Option 1 is to change the limits and use u. Option 2 is to leave the limits and go back to x. Okay, so we're going to do it both, and then you guys can just pick whichever one you want to do. But the picking of the u is the same no matter what. So here we're going to pick u to be, almost always it's going to be the inside function. Now notice that here the inside is 5x squared plus 3, and remember that what you want to do is you want to check to see if the derivative of that is also inside of the integral without taking into account the constant. Here I forgot to put dx, sorry. So the derivative of 5x squared plus 3 is 10x, and we have an x outside, so that looks like a thumbs up for us. So we're going to let u be 5x squared plus 3. And then we're going to start doing a shortcut for the du. We're going to jump this intermediate du over dx step and just find the derivative of u, which is 10x, and then multiply both sides by dx in one step. So this will save us some time. Okay, so then we go, alright, so we have this guy is u right here. Now we don't quite have du, we need a 10x dx, and we have just x dx. But that's no problem. I mean, we know that constants aren't a big deal. Since I need a 10, I'm going to multiply by 10, and then on the outside I'm going to divide by 10. That way I'm not changing the problem. Okay, so putting those two together, 10x dx, those two put together are du. So then what I'm going to have is, well here, okay, so here we have to decide, are we changing the limits or are we leaving the limits? So let's do, we're going to do it again, we're going to do it both ways. So we're going to do the first way, we're going to change the limits and use u. So if we're doing it the first way, you're going to change the limits from 0 to 1, which are in terms of x, into u's. So first thing we do is when we say that when x is equal to 0, which is the lower one, u is going to be, we plug in 0, so we're going to get 5 times 0 plus 3, that equals 3. And then when x is equal to 1, we get 5 times 1 plus 3, u is equal to 8. So these guys are going to be, my new limits. And we're going to keep u in the end, which is different from how we've been doing it, the indefinite integrals. Okay, so what we're going to have is 1/10 the integral from, instead of 0 to 1, since I'm changing everything to u, I'm going to go from 3 to 8. And this guy is going to be u raised to the 10th power, and then these two put together turn into du. Okay, and this I can find the antiderivative easily. the antiderivative of u to the 10th is just u to the 11th over 11. And this is going to be evaluated from 3 to 8. Okay, so remember that you always plug in top minus bottom. So this is going to be equal to 10 times 11. So this is going to be, why don't I just take out, well, I'll just leave it out like this. It doesn't really matter. If you want to take out the 11, you can and multiply it by the 10. But I'm just going to leave it. Leave the 1/10 out and then leave the 11 inside. So I'm going to plug in top minus bottom. So I'm going to have 8 to the 11 over 11 minus 3 to the 11 over 11. And this is equal to, sorry I made up such big numbers, I didn't really mean to, but that's alright. This is all equal to approximately 780,88704. Okay, so 78,088,704. Okay, so that's using the first way, and that's completely fine. But now let's do it using the second option. And then you guys can just pick whichever way you want to do. Now what we're going to do, the second way, is to leave the limits alone and go back to x in the end. So we skipped this first part that we did right here where we changed it from x's into u's. And we're just going to find the indefinite integral. We just want to find the antiderivative. So we're going to start off in this step. U to the 10th du, and and then so we find the antiderivative, which is, so the 1/10 stays out, and then u to the 11th over 11. And then we go right back into, so we don't even say we're going to evaluate it from a number to another. We're just going to go back to x's before we even do anything. So we have 1/10 times, instead of u, I'm going to put what u equals, which is 5x squared plus 3 to the 11th over 11. And this one is the one I'm going to evaluate from the original x limits, which is from 0 to 1. So then this becomes, let me go back here, sorry about that. Whammo! Magic. Okay, so then I'm going to plug in top minus bottom the same, so I'm going to have 1/10. I'm just going to leave the constant out. And then I'm going to have 5 times 1 squared plus 3 to the 11th over 11 minus, plug in the bottom, so it's going to be 5 times 0 squared plus 3 all to the 11th over 11. And this is equal to 1/10 times, this is going to be 8 to the 11 over 11 minus 3 to the 11 over 11. And if we take a look and compare, these are exactly the same. Now it's just up to you. I mean, if which way you prefer. So I don't know. I'll probably, me personally, I think I like to just change it to use, but I don't know. If you want to, maybe leaving it as used confuses you, because when we have an indefinite integral, we always go back to x's, so then you would probably want to do it this way. But maybe going back to x's confuses you. It's just really up to you. But notice that you get exactly the same answer. Okay, so let's do one more example, and then you guys can do the handout videos. And those will get you right on track. So why don't we do, how about the integral of sine of square root of x over square root of x dx. Okay, so we look at this guy and we go, well, we know that we usually let u be the inside function, which would be this square root of x, but the question is, well, is the derivative of square root of x in here? We have this square root of x on the bottom, which looks kind of weird, but well, let's just start it off what our instincts tell us. So if u is square root of x, then du, the derivative of u, well, remember we have our little shortcut. The derivative of square root of x is just 1 over 2 square root of x. Then we're going to put the dx over here. And so here, let's take a look. Well, this guy is u, and we almost have du here, actually. All we need is, we're missing a 2 on the bottom, but we already know that constants we don't worry about. So if we put a 2 on the bottom, then that means we're dividing by 2, so on the outside we have to multiply by 2. Okay, so here what we have then is, this is going to be du, and this problem all of a sudden becomes solvable, because what I'm going to have is 2 times the integral of sine of u, and times all this is going to be du. And so, okay, so the antiderivative of sine, well, that's negative cosine, so this is going to be negative 2 cosine of u plus c, and then I'm going to go back to what u equals, which is negative 2 cosine of square root of x plus c. And that's it. Alright, folks, well, that's integration by substitution. This gives me a big smile on my face. Woo-hoo. And so do the handout problems, and you should be good to go to finish all your homework. Okay, goodbye.